Good morning, everyone. We start today's lecture on time. You are here to study the course about the artificial intelligence and the modern life. Today, we move on to study lecture 3. So lecture 3 will focus on a specific AI system or AI product, right? So before we enter the study of today's lecture, let's have a quick overview about what we have studied so far in lecture 1 and lecture 2. So you remember in lecture 1, we have studied the definition of AI. Also, we have studied the special history of AI. And by now, you should be able to understand what do we mean by AI 1.0, which is focused on machine thinking. And also, you know what do we mean by AI 2.0, which is focused on machine learning. And now we are in the era of AI 3.0, which is focused on machines' self-intelligence. And this slide summarizes AI 3.0, right? So you just need to remember these 1, 2, 3, 4. 1 means there is one tool, which is human language. 2 means there are two worlds. One is the external physical world, and the other is internal conceptual world, right? Then 3 means there are 3 types of intelligence, which include human intelligence, computer-aided intelligence, and artificial intelligence. 4 means there are 4 pillars for us to achieve the transformation from computer-aided intelligence into machine intelligence. And these 4 pillars include knowledge representation, knowledge perception, knowledge computation, and knowledge application, right? And we also know that the weak pillar among these 4 pillars is knowledge perception, right? And in terms of signal flow, data flow, and knowledge flow, we know any AI product or any AI system must include a pipeline of signal flow, data flow, and the knowledge flow, right? And inside this pipeline, there are 3 phases. The first phase is transformation from sensory signal to knowledge. The second phase is the transformation from knowledge to knowledge, right? For example, one type of knowledge to another type of knowledge, right? And the third phase is a transformation from knowledge to motor signal, right? So pay attention. The signal at the entry should be signal from a sensor, and the signal at the end of the pipeline of a flow should be the signal to motor or actuator, right? So this is a content that we have studied or we have learned in lecture 1. And then in lecture 2, we have studied some popular application, which could be classified into these 3 categories. The first category are application which are related to knowledge. And the second category are application which are related to skill. And the third category contains application which are related to creativity, right? And today we are going to move into the study of a specific AI system and the AI product, right? And from the study of lecture 2, we have learned a very interesting concept or very interesting business model, which is a sharing scheme, right? For example, office sharing. So we know that with the integration of AI system, we can make a building, okay, to achieve, okay, or to implement this business model of office sharing, right? And this philosophy of sharing, or this business model of sharing, could be extended to other system in our modern life. For example, we can do building sharing, school sharing, factory sharing, hospital sharing, all right? And I guess some of you should be familiar already with this concept of car sharing, right? So in today's lecture, we will study the AI system or AI technology, which will enable us to implement this business model of car sharing, right? So this should be the extra benefit for you to learn artificial intelligence, and in particular, you understand that the AI will enable us to implement or to widen or enlarge the scope of deployment of business model of sharing, right? Okay, and here we need to pay attention about the difference between rental and sharing. For example, every one of us know there is a car rental business model, right? Then people also talk about the car sharing business model. So we must pay attention to the difference, right? Renter means you must go to an agency to do a booking, to rent a car. Then you need to pick up the car. After the usage of the car, you must return the car, right? But for sharing scheme, is not exactly like that, right? You can do the online booking in real time. Then the car will come to you. That means you do not need to go to a specific fixed location to pick up the car. Okay, instead, the car will come to you, right? And after the usage, you can release the car at any location. You do not need to send the car back to a specific location in order to return the car to agency, right? That is the difference between car rental and car sharing. And you see AI actually will make us to achieve this business model of sharing, because AI will make a car to be intelligent so that the car can come to pick up the customer, and the customer can release the car at any location, right? So you see the difference between car rental and the car sharing, okay? And similarly, you can start to think about the AI system, AI product, which will enable building sharing, house sharing, school sharing, etc. Right? Then try to think about the use of a humanoid robot, because when we use a humanoid robot, eventually we may be able to achieve building sharing, car sharing, school sharing, hospital sharing, etc. Right? Okay, so this should be an interesting business model. Okay, and today we will move on to study lecture 3, which is about a specific AI system or AI product, right? And this AI product is very, very popular to all of us. I guess every one of us know what is a car, what is a vehicle, etc. Right? Okay. And interestingly, people have already talked about the car sharing, all right? in terms of philosophy behind the business model of car sharing, actually it is to achieve this objective of zero ownership, right? And here you see the use of electric vehicle. Actually, the deployment of electric vehicle will help us to achieve zero pollution, right? Okay, so zero ownership and zero pollution, okay, should be a very, very interesting objective for us to achieve in our modern life, right? So besides these two objectives, the third objective which could be achieved with the help of AI system or AI product should be zero accident, right? Because vehicle could cause accident. Then how to achieve zero accident? Okay, that should be a very, very interesting objective for us to reach or to achieve. You this for us to achieve. So, this objective only power the help system or AI, right? Okay. So then for lecture 4, we will study another specific AI system or AI product, which is a humanoid robot. Okay. So then for the assessment of this course, this slide highlight to you about the component inside the assessment, and also the class participation will give you extra bonus in the assessment, right? And the way for us to assess you about the learning outcome from this course is for you to do a mini project and to submit the report of your mini project. And inside the mini project, you are expected to present or to write or describe AI system or AI product which will solve engineering problem or addressing the social need, right, with the use of your AI system or AI product, etc. Okay, in case if you do not know how to start with your mini project, then you try to study this slide and think through the answer to all these questions. Okay, when you make the attempt to answer all these questions, I believe you will know, okay, what to do, what to write inside your mini project, right? So once you have an idea about what to do, what to write, then try to follow this guideline to structure your report according to this sequence of chapter, right? So this slide basically help you to understand what should be the standard layout of any engineering report or research report, right? So you use this opportunity to sharpen your skill in writing engineering report and the research report, right? Okay, now we start the lecture 3 in this course. So lecture 3 is for you to learn slightly in more detail about the popular and the specific AI product or AI system, which is autonomous vehicle. I know that some of you do not have engineering background, but it does not matter. So you just need to know, okay, in order to develop autonomous vehicle, which is a specific and popular AI product, we need to apply all these engineering knowledge and skill, etc. Right? And you just need to focus on the benefit with the achievement of autonomous vehicle, for example, car sharing scheme. So for those of you who do not have engineering background, so you just focus your attention on the benefit with autonomous vehicle in our modern life, right? Okay, so I just skip the slide which give you a short introduction about myself. And this slide will help you to understand my educational background and also my research expertise area, right? And the domain, etc. Right? Okay. And this slide highlight to you some of robotic projects that I have undertaken, and in particular, I have also undertaken research projects which are related to the development of autonomous land vehicle, and these are some research achievement from my research. And from this slide, let you see, I have also participated to this international collaborative project which involve University of Tongji and the University of Fudan and the University of Michigan State University. Okay, also the Nanyang Technological University.
今天在内竞赛，作品及自然科技
On top of project which are related to the development of autonomous land vehicle, I have also undertaken projects which are related to the development of autonomous water surface vehicle, right? So this slide showing you one of the platform that we have developed, okay, in Nanyang Technology. Right? So help you to innovation and the major okay involve development of vehicle and also opportunity for you if you would to research, right? Okay. Today's study is for you to know the okay government right all what are the technology of autonomous vehicle, the key technology behind perception and control. And want to research we know that our also for from high speed capacity from location in and us certain area. Okay. With the of for more with ease suffer from trying to get accident and in certain will also high cost of the car and also high cost of paying for parking. So these are the common problem caused by the it is to minimize the negative impact of this to eliminate this right. But interesting enough, actually help to overcome these cost transportation system. Okay. And car accident, I guess every one of you know, right? So from this picture, you know what is what do we mean by big accident? So when there's an accident, then there's a lot of damage and loss in terms of income, revenue, and property, asset, etc. Right? And okay, here is one more example. This happens in year 2011, right? So with a single accident, then you see there's a huge amount of loss, right? Because this accident involved a Ferrari, one Lamborghini, and 5 other vehicles, right? So such accident caused a huge loss to the owner of the traffic accident. Right? So you was achieve future zero and you I achieve zero. What are the which are the achievement of accident? So in this slide, I'm going to show you the history of autonomous vehicle development. And interestingly enough, the history of autonomous vehicle was dated back in 1939. All right. So this is this history was started very, very earlier. But every one of you know at that point of time, we do not have an embedded computing system. We do not have a digital computer. All right. Obviously, the objective set by people in year 1939 was too ambitious. Actually, was not possible to achieve at that point of time. Okay, and it is only in 1980s with the advance of technology developed in robotics, and when people start to apply robotics technology into vehicle, then really we start to see the progress towards the development of autonomous vehicle, right? So then from this timeline, then you see in 1984, 1987, CMU is a USA university, has a project, right? With a focus on the development of autonomous vehicle. And then almost more than 10 years later, the industry started to show their interest in the development of autonomous vehicle. For example, in year 1998, Mercedes-Benz, Toyota, Mitsubishi, etc. start to venture into the development of autonomous vehicle, right? But however, we must pay attention in this timeline. There is an important missing entry, which was about the world's largest project dedicated to the development of autonomous vehicle. And the name of this project was Eureka Promises. Eureka Promises was started in year 1986, right? So until today, Eureka Promises is still the world's largest initiative dedicated to the development of autonomous vehicle, right? Okay, and in year 2014, here you see in year 2014, the company Tesla started to venture into the development of autonomous vehicle. And in the same year, the initiative which was dedicated to the development of autonomous surface vehicle was started with the RoboX challenge, right? So then you see this initiative dedicated to the development of autonomous surface vehicle was also missing in this timeline, right? Then from year 2017 and all the way into the future, for example, into year 2030, right? So these are the timeline, okay, which showing you the objective or the target to be achieved by the company, okay, in the world, right? Another important event is this the driverless car competition or DARPA Grand Challenge. DARPA is an agency which belongs to the U.S. Department of Defense. All right. So in year 2004, all right, is another important initiative which was dedicated to the competition of a driverless car. Right. And this initiative was supported by DARPA, okay, which is an agency inside U.S. Department of Defense, right? Okay, and from this slide, then you see BMW and launching fully autonomous vehicle in year 2025, and Hyundai aim to launch a fully autonomous vehicle in year 2030. Right? Okay, as I mentioned, in the timeline of the history of autonomous vehicle development, this world's largest initiative was missing, okay? So it is very important for you to remember, right, Eureka Promises project, because it is the world's largest initiative, right? And this project was started in year 1986 with the participation of all the major car makers in Europe, all the major research institutes in Europe, all the major universities in Europe, right? Okay, and this video gives you an answer about this world's largest initiative, right? And this video in French, but it doesn't matter. You just watch the video, then you will understand roughly what is this Eureka Promises project about, right?
Technique mobile le moyen de trouver matière de sécurité. Priorité de des obstacles peut assurer sur des véhicules. Après environnement. Ainsi, le secteur automobile facilite dans le son nom est juste. Les circulations pures éléments nécessaires. Les de 5 pays européens aujourd'hui et plus d'une centaine de projets. Les autres les travaux. Le docteur Volvo la notion de bien aspect.
Perfect finals and options. This is slowly
de la réussite de
the first real industry and supplier industry. If that will be ways to come.
Le technique du comité et autres gouvernements européens causant automobiles sont le gros des institutions. Enfin, de conçoir la question de programme est entièrement c'est un capteur signal général système aléatoires de la normes.
Okay, this should be good enough. We should give you idea about the scope and the objective of this world's largest initiative dedicated to the development of autonomous land vehicle, right? And I was a part of the team in France, which has participated to this Eureka Promises project. And this video highlight to you our research work done for Eureka Promises project. I was with then in year 2004, there is another initiative which was supported by DARPA. DARPA is an agency inside U.S. Department of Defense, right? And this grand challenge actually is a driverless car challenge, right? And in total, there are 3 competition, right? And we have participated. We have made an attempt to participate in year 2007, right? And this video highlight the second driverless car competition supported by DARPA grant.
Yeah. Visualization way. Number
the okay, so that should be good for you to understand the objective and the score of a competition organized by DAPA for its grand challenge, all right? And actually in year 2006 and 2007, we have made an attempt to participate to DAPA grand challenge, all right? So we have formed a team with people from Tongji University, Fudan University, Michigan State University, and Nanyang Technological University, all right? And the financial support was provided by Tongji University. This is why you see the vehicle or the hardware platform was deployed inside the campus of Tongji University. And finally, Tongji University has made this publicity video which summarizes what we have done during the period between year 2006 and the year 2007.
它的 GPS 在路径上驾驶的各种任务。分别来8月初的1年多发展方式和形式，每月投入 妹妹颜色切换作品中少女气球大件高超车技术其研发下和车一体是想场馆按键动点击便能自动安使用常见的操作。
In you can stay subsequent team your company to the min income right like rob and also know like Google and some other company okay, which also venture into the development of autonomous vehicle. Okay, and this slide this should be good enough, right? And besides the public transport with the use of bus, lorry, or private car, then in some specific locations, such as a port, the seaport, we also deploy autonomous vehicle to support the transport of container from one location to another location. Then in this way, AI will enable us to achieve this scenario of unmanned port. And this video will highlight to you about this. There you see a lot of land which see or in 2014 there are many challenging tasks for autonomous surface vehicle to undertake. For example, passing through two designated gate, right? You have an entry gate and the exit gate, right? So let the vehicle to autonomously travel from the entry gate and the exit from the end gate, right? And this is a scenario for autonomous vehicle to achieve this behavior of moving around specific target without the collision with other object in nearby water area, right? And this is a similar scenario to the automatic parking on land. We may also enable autonomous surface vehicle to have this capability of doing parking or docking to a floating platform, right? So this is a scenario of achieving autonomous docking. Okay. To dock autonomous surface vehicle into a docking bay, right? So we use this terminology. So it's not parking lot, right? Here we call it as a docking bay. We have a bay 1, bay 2, bay 3, right? Okay. And this is to develop the autonomous capability for surface vehicle to observe dynamic feature in the scene. In this case, we want the vehicle to be able to record the color sequence, okay, emitted by the lighting tower, right? And this is a task for vehicle to observe or to identify or recognize familiar object placed on the seabed, right, or riverbed or waterbed, right, okay, at the bottom of the river, okay. And this is also a task for autonomous surface vehicle to identify the structure installed on the seabed or waterbed or riverbed, etc. Right? Okay, and this is to demonstrate autonomous surface vehicle capability to deliver object into a warehouse which flow on the water surface, right? And this is another competition task which requires the autonomous surface vehicle to be able to hear, all right, to detect the presence of an emitter of acoustic signal, and based on the detection result, then the autonomous surface vehicle must undertake a specific behavior or task, right? Okay. And this video summarizes what we have done for year 2016's competition.
其实
Will give you an idea about the development and the research activity undertaken by different team member from the team in year 2016. And this slide give you some picture about the test of this vehicle in the leg of our university. Okay, and this slide showing you some video about the real competition side in Hawaii. With autonomous surface vehicle, and it's like the situation for the development of autonomous land vehicle. Actually, there are also many initiatives supported by industry for the development of autonomous surface vehicle. And here I just showing you one example from a company in Singapore, which is a national company in Singapore.
Might not for you and I need to know that was cutting see US hospitals. To that, that's where event is
Then initiative autonomous how we maker was to achieve was zero, and we also there are many company is want to study or land vehicle. Most students engineering your result most of background try to think about the we cannot to planning control. And eventually you need to spend study at least to lead. Okay, before we go through an overview about perception, planning, and control, we may want to know, okay, what do we mean by autonomy, or what do we mean by autonomous vehicle, right? Without knowing this answer, you may not know why do we need to deploy perception, planning, control inside the vehicle, right? So then with the answer to this question of what is autonomous vehicle, then you will appreciate the role played by each module of planning, perception, and control, right? So in the public domain, if you ask this question to general public, what is an autonomous vehicle? I guess you will receive all kinds of answer, right? And in general, there are three typical answer to this question. One type of answer is automation centric. People think in terms of automated function, automated task. All right. If we are able to achieve one automated task, then we say this vehicle has reached level 1 of autonomy. If the vehicle could perform two automated function or task, then we say this vehicle has reached level 2 autonomy, right? Or if the vehicle could eventually undertake automatic driving, okay, then we say this vehicle reach level 3, okay, autonomy, all right? And if the vehicle could achieve 100% automatic driving, then we say this vehicle has reached level 4 autonomy. And if let's say this vehicle could drive itself without the presence of a human driver, then we can say that this vehicle has reached level 5 autonomy. Okay, so this is one type of typical answer to this question. The second typical type of answer to this question is to focus on operation. For example, if this vehicle is fully operated by human driver or partially operated by human driver, then we just say that this vehicle has reached level 1 or level 2 autonomy, all right? Then slowly the level of autonomy will increase all the way when the vehicle could fully drive itself, all right? So this is another way to define a different level of autonomy, okay, from the viewpoint of operation, okay? And the third way of answering this question is look at the degree of autonomy, okay, from partial degree of autonomy to 100% or full degree of autonomy, all right? This is a product-centric way of viewpoint about the autonomy. I believe this answer should be more relevant to industry or to the market, because here we talk about developing autonomous vehicle as an AI product, right? So we offer this assistant, offer this product to the buyer, to the user. Then user may want to know, right, the degree of autonomy, right? For example, if this is a vehicle could achieve 100% control of velocity, 100% of control of steering in all situations, then we can say that this vehicle achieve level 1 autonomy, right? Then in addition, if in future this vehicle could 100% undertake trajectory following in all situations, then we can say this vehicle has achieved level 2 autonomy, right? And on top of this existing level of autonomy, if let's say in addition, the vehicle could 100% undertake collision avoidance in all situations, then we can claim that such a vehicle has reached level 3 autonomy, right? Then we can continue to add in additional behavior to the vehicle. For example, if the vehicle could undertake 100% lane changing and slow moving vehicle takeover, right? We take over slow moving vehicle in all situations, and then such a vehicle could be considered as reaching level 4 autonomy. And lastly, with all the previous capability, and if the vehicle could also 100% undertake sequential parking, parallel parking in all situations, then we can say that such vehicle has already reached level 5 autonomy. All right. Then with all these capability, I believe the vehicle should be able to drive on their own in all situations. All right. I believe this type of answer should be more relevant to the car maker, to the car buyer, because to the car buyer, they can make a decision. If let's say I buy a car which is at the level 3 autonomy, then the buyer immediately know, okay, what should be the capability, okay, with the purchase the car, etc. Right? Okay, so this just for you to know. And from this answer in this slide, immediately you know, okay, what should be the outer control loop, which involve perception planning and the control, right? To do, right? Because for each function or capability listed in this slide, we need this outer control loop, which involve perception planning and control. So now you see the key technology development of vehicle, more technology, time, passion, technology behind. So now let's go through them one by one. Okay, so we start with perception. Okay, so perception basically is to know the environment in the surrounding of our vehicle, and this information is extremely important for the vehicle to undertake planning and control. For those engineering enjoy be able to use the actually vehicle knows the motion. Okay, and this slide basically highlight to you about the visual capability of autonomous vehicle for the identification or recognition of a color belong to the surrounding environment, or identify the color belong to the vehicle, or identify the color which belong to the road, etc. Right? This is a way to understand the content in the raw image on the in the raw environment, right? Okay, and this slide is help you to understand that the autonomous vehicle must have visual capability to identify empty parking lot and also know the geometry of empty parking lot. This should be the input to the planning module so that the autonomous vehicle will be able to plan the motion equation, which will the input to the control system. All right. So with the motion equation, then the control module should be able to control the motion of the vehicle. Right. Okay. And this slide highlight to you the perception capability of autonomous vehicle in the 3-dimensional space. All right, it is like a human driver. Human driver heavily make use of a binocular vision system, right, to determine the 3D geometry in our surrounding environment. All right, for a vehicle is the same, right? So the vehicle will use a binocular vision system to determine the depth information, and here we have developed an inverse reconstruction solution. Okay, for those of you with knowledge about the computer vision, then you should be able to understand this slide. But for those of you, if you do not have computer vision knowledge, and this slide will motivate you to study the course about the computer vision. All right. So basically, we have a two camera, and you just need to know for each camera we have an equation which relate the XYZ coordinate to UV coordinate. All right. If we know XYZ, we can compute UV. If we know the UV, we can compute XYZ. All right. But here we make assumption about the discrete value of one of these XYZ. For example, Z is equal to a series of discrete value. Then for each value of Z, we can compute XY from left eye, right? Then once we know XYZ in the scene, then we come to the right eye. Then we can use XYZ to compute UV in the right eye. Okay, then in the left eye, we know UV. In the right eye, we also know UV. Then we need to verify whether these two UV are matched together or not. Okay, if these two UV from the left eye and the right eye come from the same XYZ, then this XYZ should exist in the 3D environment. All right, so this is the working principle of this solution. This is a very, very powerful solution in computer vision. All right, so for those of you, if you have an interest in visual perception, you must fully understand this slide. Okay, so and we have also developed qualitative binocular vision. All right, from this curve you will see horizontal axis indicate the measurement of disparity, and the vertical axis indicates measurement or estimation of depth. Then what is a disparity? Disparity basically means the UV coordinate in the right eye minus UV coordinate in the left eye. Okay, so UV in the right image minus UV in the right image is equal to the disparity, right? Is this horizontal axis. Then it turned out that the depth information has this very smooth relationship with the disparity, right? So we can predetermine this curve, then we call it as a lookup table, right? Then during the real operation from the image processor, we can determine disparity. Then from this curve, then immediately we can find out what should be the value of depth, right? Okay, so for those of you who have an interest in visual perception, you must remember this slide and know this possibility of determining depth information in a qualitative way, right? Okay, so, and this is also one of our patented technology. This is to make use of 4 video to synthesize a single video. And this single video is equivalent to the video output from a camera placed inside the sky and look down to our vehicle, right? So you see, it looks like a to our vehicle, right? And video from a camera mounted on the vehicle to produce such a output of a video which is equivalent to the video which is the output from a camera placed in the sky and which look down to our vehicle. Okay, so this is also interesting result. Okay, then for other things research work, I guess last lecture we have already showing you video. I just and that's about the surface vehicle, right? After the planning, right? And here you see the outer loop of any autonomous surface vehicle or land vehicle, right? After perception, there must be a planning module. So input to planning module should be the knowledge about the geometry in the surrounding of our vehicle. The output from the planning should be motion equation, right? To be executed by the vehicle. Okay, and here I highlight some important research results achieved by our team. Right? First is this XI coordination. Right, so we use a binocular vision system, and we managed to discover this simple relationship. So it tells that if we have a motion or relative motion of the camera, okay, in 3D scene, which is represented by the vector of theta x, theta y, theta z, and this motion will produce observe the motion inside the binocular vision system, and the observed motion are indicated by the vector of theta ul, theta vl, theta ur, theta vr. But important conclusion is between the motion of the camera and the motion of image feature, there is a constant matrix. df, di are constant matrix. All right. So actually, these two matrices serve as a planning matrix. Actually, it's a planning equation. All right. So as long as, for example, if we observe motion inside the binocular vision, then we can directly compute the motion of the camera with respect to the environment. Okay, if we use a camera as a reference, then that should be the motion of target. If we use a target as a reference, then we can compute the motion of the camera. Okay, so theta x, theta y, theta z indicate the relative motion between binocular vision and the environment. Okay, and this environment could be or relative motion could also be the motion between the actual coordinate system of a robotic hand and the expected position and orientation of a robotic hand. Then in this case, we can undertake hand-eye coordination. All right. But for today's lecture, our scenario is the second one. That means we mount the binocular vision system on the mobile platform, that is a vehicle body. Then we can imagine that the vehicle serves as a head. It's like a human being, we have a head, right? So that means use binocular vision to determine the relative motion between the body of the vehicle and the environment. In the environment could be represented by a moving target, etc. Okay, so this is a very, very interesting result and extremely important result for you to know. Okay, and this motion inside regulate motion, okay, with respect to the event, right? So interesting. Okay. And so the previous slide showing you the planning equation. These are the planning equation, right? So and directly compute the motion of the vehicle, right? So this is a motion equation, plane equation. And this is a result achieved by us. Okay, let's say we know the free parking lot and we know our vehicle's current location, which is the parking lot. Then how to plan a spatial location which will enable the vehicle to enter the parking lot. But here you will encounter one important terminology in robotics. You see path planning, right? On top of this terminology, there's another terminology in robotics which is called as a trajectory planning. So now you see we have a path planning, we have a trajectory planning, and this animation or you path planning. Okay. And planning. So the difference is concept. Path planning is the will vehicle to move the initial to reach the position, right? But why we concept which trajectory, right? So trajectory is with both space time concept, right? So maybe show you the in path planning is like and the reason we have a clear obstacle technology prevent us to develop autonomous product. Yes, the has public data function will enable a vehicle to take parallel parking, right? Okay, so actually you see we have a clear the last obstacle in technology which prevent the industry to commercialize autonomous vehicle, right? So this is a very interesting result for you to know. Okay, so it's just an inverse planning strategy, and we can also apply this inverse planning strategy to the scenario of making autonomous vehicle to undertake sequential parking. For example, in the left-hand side, we have a vehicle, okay? He has a detect one empty parking lot, and this vehicle would like to make sequential parking with head entry to the parking lot, okay? And the head entry to the parking lot means the head enter the parking lot first, okay? So then in this case, you see the outcome from inverse planning should be circle one. You see, inverse planning, we determine circle one first, then followed by circle two, circle four, then followed by circle five, okay? Then during the control, that is a forward control. Then you will see, then we will control the motion of the vehicle to follow circle five, then to follow circle four, then to follow circle one, right? So control is a forward control. Planning is a inverse planning, all right? And in the right-hand side, we see the scenario of doing sequential parking with tail entry to parking lot. That means the tail of our vehicle enter the parking lot first, okay? So then in this case, the outcome from inverse planning will be line 2, circle 2, circle 3, and line 1, all right? Then for the control of the motion of the vehicle, then you will see the control is doing forward motion, all right? First, the vehicle will perform the motion along line 1, then follow circle 3, then follow circle 2, then follow motion along line 2, right? So you see this inverse planning forward control strategy, right? Okay, so this is a very, very powerful technique, okay, for us to solve the problem of doing motion planning. You can also apply this inverse planning strategy to implement the behavior of takeover slow moving vehicle or lane changing behavior. You remember level 2 autonomy require autonomous vehicle to be able to do takeover or lane changing behavior, etc. Right? So you can apply this inverse planning strategy to achieve that level of autonomy with either autonomous land vehicle or autonomous surface vehicle. All right. Okay. And we can also have some incremental planning strategy with other type of sensor. For example, if let's say we have a car-like vehicle, remember for car-like vehicle, we just need to output linear velocity of the car. The planning module just need to output linear velocity of the car, and this is the VT and the steering angle, that is the theta t, right? And then we can use these two equations, the equation of velocity, equation of a steering angle, to do the incremental planning for car-like vehicle, right? Pay attention. This is only valid for car-like vehicle, right? But we may also have differential drive vehicle. Differential drive vehicle means we can only control left velocity, right velocity. That means differential drive, right? And here you see for land platform, we also have a differential drive vehicle by view. For surface vehicle, we have a differential drive vehicle by propulsion. We have a left propeller, right propeller, right? Then in this case, the output from planning module should be linear velocity and the angular velocity of the vehicle, right? And this slide showing you one solution developed by us, okay? And for car-like vehicle, this is also a solution developed by us, all right? So then you will see, okay, if let's say we know the current pulse of our vehicle, let's say water surface vehicle, we know the next pulse of a water surface vehicle, and inside the local coordinate system assigned to the autonomous surface vehicle, if let's say we know the position of the next pulse, XD, YD, we can use XD, YZ to directly compute the linear velocity of our surface vehicle and the angular velocity of our surface vehicle. And you can easily verify when YD equal to 0, then V equal to 0, right? You can also easily verify when XD equal to 0, then omega, angular velocity, will also equal to 0, right? Because when XD equal to 0, R will equal to infinity, then omega equal to 0, right? So this is a solution proposed by us for the incremental planning of differential drive vehicle. Okay, so that's about from the planning should be the input to the control. Then you want to know what are the key technology behind the design of the control module, right? Then we must pay attention to the difference between car-like vehicle and the differential drive vehicle, right? For car-like vehicle, we have two control rules. One is about the control of linear velocity. Another is about the control of steering angle. Now you see. And with the car-like vehicle, it is quite straightforward to implement these two control loops, because in the previous slide, you see the output from motion planning module will be desire the linear velocity and the desire the steering angle, then directly implement this control loop. Okay, then for those of you who have not yet studied control theory, and this slide will motivate you to study control theory, because you need to spend 1 semester to study control theory, right? But for those of you without the engineering background, you just need to know, right, what is a feedback control loop, right? So just for curiosity, okay. And then this video showing you the implementation result with car-like vehicle. Involved. Then, okay, you have seen this demonstration, which showing you the result from the outer loop, section planning, and the this is almost 20 years. Here you also like the and the velocity control. If you pay attention to the front, we are on the it should be good enough. Then you want to know, okay, how to control a differential drive vehicle, right? So for differential drive vehicle, you need to do a little bit extra planning, which is to translate the result of planning in task space to result of planning in joint space, right? And here, again, you encounter two new terminology in robotics: task space and the joint space. These are two terminology in robotics, all right? Then this slide may motivate some of you to do the study about the robotics, okay? From the linear velocity and the steering angle, we should be able to determine what should be the circular velocity in the left-hand side of the vehicle, circular velocity in the right-hand of the vehicle. Then use VL, VR to first determine what should be the rotating velocity of the left view and the right view, right? So once we know the VL, VR, and omega L, omega R, omega L, omega R should be the angular velocity of the left view and the angular velocity of the right view, then we should be able to activate these two control loop for angular velocity of the left view and the right view, or left propeller or right propeller, right? Okay, something like that. Then in terms of control, what should be the dynamics of view or propeller under control in task space? Now you see, we just showing you the result in task space. For example, in task space, we notice Newton's second law, right? The net force acting on the single view is equal to the mass of the single view, together with the payload. Mass of m means mass of the view plus is payload, right? And times linear acceleration, right? X double dot is a linear acceleration in task space, right? And then we can write x double dot as a function of net force divided by m, right? And the net force divided by m, we can say this comes from the motor, right? Motor is a converter which convert electric energy into mechanical energy, right? You treat the U as a output of mechanical energy, mechanical energy produce acceleration, right? Then acceleration come from variation of velocity, and the velocity come from variation of position. So that means behind x double dot, they must be x and the x dot. If we put x and the x dot into a vector, now you understand this concept of state vector, state space, right? So we have x dot, we call it as a state vector. And that state vector will produce, all the value of a state vector will create state space, right? So state space is a terminology in control theory. And this slide will motivate those of you who have an interest in doing development and the research of autonomous vehicle to study control theory, right? So in control theory, you will know what is the state space equation, etc. But actually, this slide already explained to you example about the state vector, state space, all right? So then we can remember x1 equal to x, x2 equal to x dot, right? Interestingly, with this state vector, we can rewrite this simple equation of Newton's second law into this matrix form. Okay, then you see x dot, x double dot form this vector, which is equal to capital X dot, right? Then equal to matrix, constant matrix times capital X plus another matrix times U. U you can consider as an input of a mechanical energy, right? So actually this is the state space equation already, right? And then what should be the output? Here C is a selection matrix, you just select whether x1 is output or x2 is output. That means we can let the position to be the output or velocity to be the output. If a position is output, then we are doing position control. If velocity is output, then we are doing velocity control. Now you see, and this all depends on the output y. Y Y just contain either position or velocity. C you can consider as a selection matrix, right? So this is a perfect standard state space equation, and this two equation describe any dynamic system in the universe, right? But also we get this result from this view, but actually all the dynamic system actually you can write them in its form. Okay, if you write the detail, only difference is the size of ABC will be different, or the value inside ABC will be different, right? The format of state space equation will be exactly the same, right? So you see, to study control theory is not that complicated, right? Then the next question is, how do we determine the amount of mechanical power to inject into our vehicle in order to control the steering angle, control the linear velocity, all right? So now you see, we just use this philosophy of producing amount of energy to control the dynamics based on the equation of error. And this equation of error is, or the error is the difference between the desired output and the actual output. Then in this case, you will see error is 0 minus y. The desired input is 0, right? We do not want the position to change or velocity to change, for example, right? So this could be preset the position, preset the velocity. Then we can treat as a 0, right? Because if it's not 0, we can cancel, minus out the constant, bring it to 0, right? So mathematically it is equivalent, right? Then 0 minus the actual output is what? Error. Okay, this is a philosophy, very important, very simple philosophy in control theory. That means we determine amount of energy to A in based on the function of error, right? And there are three typical type of function for us to use. One is a proportional function, second one is integration function, and the third one is a derivative function, all right? If we combine them together, then you may have heard of this terminology of PID controller, right? So P means proportional, I means integration, D means derivative, right? But here we just showing you the result of using P controller, proportional controller. Then K is a control gain for the proportional controller, right? And when we design a control system, the designer has a freedom to choose the value for K. Then the question is, what should be the value for K so that this system will become stable, right? So then we must substitute this U with a negative Ky law. Okay, then we rewrite the equation, lump all the matrix together. Then we have x dot equal to a prime x. Actually, this is a very simple equation, right? So in time domain, the solution is x t, time function of x equal to e raised to the power a prime t. And e raised to the power a prime t. So a prime could be decomposed into eigenvalue and the eigenvector, right? So then for this system to be stable, the eigenvalue must be negative. That means if let's say in the S domain, but then this will introduce you this concept of a Laplace transform. This way, this is why you need to spend one semester to study control theory, right? So in the frequency space, we call it as a frequency space, right? So the eigenvalue must in the left half plane, right? Left half plane means horizontal component of lambda must be negative. So this you see RE, capital R, small e means a real component. Real component means a horizontal component of vector lambda, right? Okay, and some background knowledge is in this slide. If for those of you, if you do not know what is eigenvalue, eigenvector, this is just explanation. That means for any matrix, you can always find a series of a vector so that the A times vector V equal to lambda times v, magic journal, right? So lambda is an eigenvalue. Then such a v is called eigenvector, right? Then we can use lambda I1, 2, 3 to form a diagonal matrix, and the v to form any matrix like a V matrix. Then any matrix A can be written in the form of A V times D times V inverse, right? So this is the decomposition of any matrix into diagonal matrix, okay, together with two other matrix. One of them is the inverse of a V, another is the V itself, right? So D is a diagonal matrix, okay? So once we have a diagonal matrix, then we can, okay, decouple, okay, the effect of lambda 1, lambda 2, etc., right? Okay, so it's just for you to know. And then from this slide, if you want to know more detail, that give you motivation to study control theory, right? Okay, so that's the study of technology behind each is more you to study at least one semester, right? So actually we cannot cover all the knowledge, right? Okay, and you may want to know, okay, is there any opportunity for some of you to take research in this area, right? The answer is yes, but you must pay attention, right? Try not to confuse between research work and the engineering work, right? If you just implement the solution developed by others, that will be engineering work, right? You should not call them as research work. And research require you to achieve a better result, right? So then you may say, how to understand research? You just need to remember this again, 1, 2, 3. Research has one objective, which is to achieve a better result. Or you can say research has one keyword. This keyword is better, right? And the research has two driving force. And here you see two driving force. One is a scientific problem, which look for solution or look for better solution, or social need, which also look for better product or better system, all right? Then 3 means what? Research will produce 3 type of a better outcome, either better theory or better technology or better product, all right? So you must understand the nature of the research before you will make a decision to venture into the development of a research of autonomous vehicle in future. Right? In this area, plenty room for you to consider how to in future to understand the meaning in the place about the road or in the along the side of the road. Right? So you see, of a detail vehicle, a lot of information, and all these supposed to be in many different language, right? Also another future research for you undertake, etc. Right? And in particular, okay, we can also venture into the level which will make a future vehicle to achieve self-intelligence. Then in this case, in future, you should be able to undertake a conversational dialogue with vehicle, right? So in today's study, you will see for autonomous vehicle as an AI product, the most important signal at the input should be visual signal, right? So you understand with the use of a visual signal, it should be good enough for us to achieve autonomous vehicle as an AI system or AI product. But nothing prevent us to enable future version or future generation of autonomous vehicle to have mental capability to understand the meaning inside audio signal. Like in this way, the driver, human driver eventually could talk to the vehicle, or the passenger inside the vehicle could talk to the vehicle, right? So you can imagine these kinds of scenario, right? So there are plenty room for you to continue, okay, the research and the development of AI, and to increase the level of intelligence of future vehicle, right? Okay, and another thing for you to know is, as I mentioned, if when we look at the timeline of development of autonomous vehicle, okay, you remember, okay, it is only when we start to okay, to make use of robotics technology into the vehicle, then we see the real progress of making vehicle to be autonomous. So it means actually robotics is extremely important, right? Is robotics actually will drive the development of a vehicle into higher level of intelligence, all right? And to a certain extent, we can say that today's vehicle could be considered as a high-speed mobile robot. So it means we can consider a vehicle as a part of a robot, right? Or mobile robot, etc. Then automobile industry in future will become part of a robotics industry, all right? So this observation will encourage you to pay attention to robotics, okay? And in particular, I believe the rise of robotics will drive AI research, okay, continuously without fall into wave. You remember AI history, okay, from the study of lecture 1, okay, AI history include 2 winter, all right? So I believe with the rise of robotics, AI will never enter into the 3rd winter. Robotics, all right? Then from this slide again, then you see robotics actually already reached this stage, which will make today's robot to achieve human-like intelligence, all right? Then this development will push AI to move into the direction of achieving machine intelligence, all right? So try to remember this trend, and then you, for those of you, if you want to do research, then you know what to do, okay? What should be the research topic for you to pursue in the future? So, like today lecture, the development of autonomous vehicle, we also major initiative behind the autonomous and behind the development of surface behind the key technology, behind the key technology, behind the technology, outer room and of control the road be able to me, okay, in future plenty room to contribute. Thank you for your attention, and I'm looking forward to seeing you in the study of lecture 4.